Okay, sorry about that. We got a bit confused with the setup here. Okay, thank you very much, Professor Watanabe. You can start when you're ready.
Thank you. So, may I start now?
Please do, yep.
Yeah, so now let me start my talk. The title of my talk is Mathematical Background of Artificial Intelligence Alignment. So first of all, I would like to thank Professor Fu Grant, Professor Dr. Fu Grant, and Professor Dr. Lin, and Professor Dr. Marfet, and Professor Dr. Oldenziel for thank you for your invitation to this conference. So this is a content of my presentation. Here, a mathematical viewpoint of AI alignment and regular and singularity and learning process and conclusion. This is my schedule of today's presentation. So let me now go on to my first point. The first point is mathematical viewpoint of artificial intelligence alignment. So you know very well, artificial intelligence research is progressing so rapidly today that we do not predict to which direction AI takes us. Here, we are here, and we do not know the prediction. It is said that alignment of artificial intelligence is necessary for safety and welfare of human beings in the near future. So what is artificial intelligence alignment? I think there is not yet the definition of AI alignment, but sometimes AI alignment is sometimes defined as AI working without deviating from the designer's intention. Today, I talk about this point. In order to consider AI alignment, we need all opinions from all different points of view. However, in this presentation, the presenter, me, would study AI alignment from a mathematical point of view. It is one point of view, and so we need all opinions from all different points of view for AI alignment. So this is a rule of mathematics in AI alignment. Yeah, so artificial intelligence have many problems, but they are very few here. By mathematically considering the desired properties of AI required in AI alignment, it might be possible to understand the problems and the challenges more clearly. So here we have mathematically defined challenges. Now let me now go on to the second point, regular and singular. Here, machine learning can be understood as a statistical estimation of unknown uncertainty by a probabilistic model. Here, this is input X and this is output Y, but this is unknown uncertainty. This is a statistical model or deep learning. This is X, and this is f of X. This is a function of X with a parameter theta, and sometimes it has these noises M. So unknown uncertainty is approximated or estimated by using this statistical model or neural networks. It is called a neural network. So learning is represented by steepest descent for the squared error. Squared error is theta is defined by the sum of the squared error of this is a norm, and so yi minus fxi and parameter theta. This is a function of theta, and the squared error, the optimal parameter theta might be found by a steepest descent by minimizing this theta. Or the posterior density in Bayesian inference, the posterior density is defined by the P of theta for given data. This is a prior distribution theta, and this is a posterior, this is a likelihood function of theta. So this slide explains the classical models and typical modern learning machines. The typical classical model is given by this equation. Here, f of x with parameter theta is equal to the linear sum of theta k and xk. Xk is a polynomial. Deep learning is given by this equation. F of x and parameter theta is equal to activation function theta. This is nonlinear function theta 1 and nonlinear function theta 2 and nonlinear function theta 3 and nonlinear function theta 4 and nonlinear function theta 5 and x and so on. So deep learning has a deep hierarchical structure. Modern learning machines contains hierarchical structure or hidden variables, which have both advantages and disadvantages for artificial intelligence. So this is a definition of identifiability. As a statistical model is called identifiable. The following map is 1-to-1. Here, this is a map, this is a parameter, and this is a probability distribution. This is a map from a parameter to a probability distribution. If this map is 1-to-1, then a statistical model P is called identifiable. In classical models, the parameter is identifiable. The role of the parameter is uniquely determined, which can be interpreted in general. However, in modern learning machines, the parameter is non-identifiable and over-parameterized. The role of the parameter cannot be interpreted in general. This is a difference. So this slide explains the regularity condition. A statistical model is called regular if the flowing matrix I theta is invertible. This I theta is called Fisher information matrix in statistics. Here I theta is the expectation of x. This is expectation over input x, and this is a differentiation with theta fx theta, and this is a differentiation fx theta, and here this is transpose. This T shows the transpose. In classical models, both the maximal likelihood estimator and the Bayesian posterior distribution converge to the normal distribution and the sample size n tends to infinity. Its preciseness of inference can be measured by using inverse of this Fisher information matrix. So a Fisher information matrix has sufficient information to study the classical models. However, in deep learning, more than 90% eigenvalues of I theta are zero in general. Fisher information matrix does not have sufficient information for statistical inference. These are the elemental difference between regular models or classical models and deep learning. So this figure explains a figure of the, this is a square error, and the horizontal surface shows the parameter set, and the vertical axis shows the square error. This is a classical statistical models. In classical statistical models, the role of the parameter is uniquely determined. By checking the parameter, we can examine whether the model is subject to the designer's intention. So the parameter has sufficient information for the designer who examines the statistical model. This is a this is a square error of deep learning. Here, the horizontal surface is a parameter theta, and also this is a square error. In modern learning machines, the role of the parameter is not determined. Even by checking the parameter, we cannot examine whether the model is subject to the designer's intention. Here, this parameter is almost equal to this parameter as a function. This parameter is almost equal to this parameter as a function. Thus, by examining the parameter, we cannot know whether the model is subject to the designer's intention. This is an elemental difference. So this table is a comparison of classical and modern learning machines. here, this is a classical model, and this is deep learning. Parameter is identifiable, and a parameter is non-identifiable in deep learning. So in order to study classical models, the necessary algebra is linear algebra. However, in deep learning, we need ring and ideal. Set of parameter can be understood as a manifold in classical model. However, as a set of parameter of the deep learning, the algebraic or analytic variety in general. So, in order to study asymptotic properties of classical model, we need Laplace approximation of the posterior distribution. On the other hand, in deep learning, Laplace approximation cannot be applied. So instead of Laplace approximation, we need elephant zeta function. Elephant zeta function has sufficient information for to study statistical asymptotics in deep learning. So probability theory, in classical model, central limit theorem plays a central role in the in study of the classical model. On the other hand, to study deep learning, we need empirical process theory. Empirical process theory is a central limit theorem on the Baraha space or function space. So this empirical process theory is a functional central limit theorem, and we need this theory to study deep learning. And address statistics, so classical model can be studied by using regular theory. However, deep learning, to study deep learning, we need singular learning theory, as you know very well. So advantages of non-identifiability in machine learning. These two properties are advantages. Learning machines, which contains hierarchical structure, has an ability to approximate much more set of functions than the classical statistical models. Even if a learning machine is over-parameterized, so the generalization error is made smaller. So over-parameterized means that the learning machine is redundant to approximate the unknown true distribution. However, in this case, even in over-parameterized case, the generalization error is not so large in general. So this slide explains the disadvantage of non-identifiability. Even if two artificial neural networks answers almost the same output to the same input, their parameters are quite different from each other. It is not ensured that they answer almost same output from unknown inputs. So different parameter. This neural network and this neural network has different parameter, but they output almost the same output for the same input. However, for unknown input, it is not ensured that they answer almost same output in general. This is disadvantage of non-identifiability. Alignment problem caused by non-identifiability. In classical statistical models, we can check whether the model is designer's intention or not by examining the parameter. In deep learning, many different parameters show the almost same learning result. Different learning results are obtained for the same training sample. Do almost same results ensure that the same output for unknown input, which are different from probability distribution used in training. So this is a mathematical challenge in artificial deep learning alignment. So let me now go on to the side point, singularity and learning process. So I think you know Bayesian statistics. So in all the Bayesian statistics, in the in the 20th century, it was assumed that uncertainty can be captured by a statistical model, and the personal belief was represented by a prior distribution. This is old treatment of Bayesian statistics. In modern Bayesian statistics now, we are aware that a statistical model is only a fictional candidate, which is different from the data generating process, and that the prior distribution is not any belief of a person, an agent, or an artificial intelligence. So prior distribution is also a statistical model. Remark, so a statistician could predict that when an artificial intelligence model makes the artificial intelligence model, AI research will be accelerated. So the artificial intelligence also make a statistical model and also make a prior distribution. In classical models, Bayesian posterior converges. Here, n is sample size, n is sample size, n is sample size. In classical models, the posterior distribution concentrates on the base parameter as n tends to infinity. The posterior distribution seems to represent a gradual increase of confidence in classical models. However, neural networks have many singularities in parameter space. Here you can find singularity and you can find singularity. So this set corresponds to this statistical model, and this set corresponds to this statistical model, and this set corresponds to this statistical model. So neural network has hierarchical structure, and it contains many statistical models in one statistical model. Parameter space of this is parameter space of a neural network. This is a learning process of a modern learning machine. In modern learning machine, the posterior distribution jumps from a singularity to another singularity. Here, this is a sample size, and this is sample size, and this is a sample size is equal to infinity. In this case, the posterior, you can find the posterior distribution here, near singularity, and you can find the posterior distribution here, another singularity. And if n is infinity, then the posterior distribution goes to here, but infinity is far from the finite sample size. Even if the sample size is huge, it is far smaller than the infinity because the deep learning has very big or huge learning machine. So the posterior distribution jump here from here to here. So such jumping process makes it difficult to diagnose whether the learning process is out of order or not. In this case, posterior distribution does not behave as this. It jump from here to here. This is a phase transition. So this figure explains a phase transition caused by free energy. Here, the horizontal line shows the sample size, and the vertical line shows the free energy. The free energy is equal to the minus log posterior probability of a parameter space. Here, the free energy of local free energy of model 1 and model 2 and model 3. Here you can find a critical point, and the model which makes minimum free energy is chosen by the posterior distribution automatically. Thus, this is a mathematical structure why the jumping process from here to here occur. So here, in this critical point, jumping process occur, and here you can find this in this critical point, the jumping process from here to here occur here. So the free energy is different from generalization error. The best singularity for the minimum prediction error or a minimum generalization error is different from the minimum free energy. So the jumping process is caused by choosing the minimum free energy, but it is different from the minimum generalization error. here you can find the sample size here, the horizontal line, and the vertical line is generalization error. So this is a changing point, but here this is the behavior of the generalization error. So this is a learning curve of a complex model. Here N is the sample size, and this is a generalization error. We can observe this learning process caused by singularity. In deep learning, the posterior distribution jumps from singularity to another singularity. This jump is optimal for the minimum free energy, but not optimal for the minimum generalization error. Free energy and the generalization error are not equivalent to each other in general. So this is alignment problem caused by singularity. In modern learning machine, the learning process, as the increase of the sample size is jumping from a singularity to another singularity. Even if the sample size is huge, it is far smaller than the infinity. Learning always remains in a singular state. It is difficult to diagnose whether the learning process is out of order or not. So the second mathematical challenge is to make a method how to distinguish the proper jumping process caused by posterior distribution from the state out of designer's intention. So we have to distinguish these differences. Thank you for your attention. This is a conclusion of my presentation. So this is a conclusion. Modern artificial intelligence have two advantages. They can be much more functions than classical models. Generalization errors are smaller, even if they are over-parameterized. The advantages are derived from no identifiability and singularity. So these advantages are derived from no identifiability and singularity are caused by hierarchy. It also causes a disadvantage for AI alignment. We need mathematical challenges to overcome these problems. So all of us hope that artificial intelligence would be useful for safety and welfare of human beings. So this is my presentation here. Thank you for your attention. Thank you. Thank you very much.
Thank you very much, Professor. This is Daniel here. I have questions, but I think who would like to ask a question, please state your name before you do so. Okay, I'll ask my question then. Okay. What do you think are the most important open areas for research in singular learning theory over the next 10 years? What would you really like people to work?
The most important. So it is very difficult question, but I think now we use a very large model. So singular learning theory can be applied to a very large model, but the conventional singular learning theory explains a not so large statistical model. From the mathematical point of view, it may make an algebraic geometry in infinite dimensional space.
Nice answer. Okay.
So I think it is important but very difficult problem. This is in mathematics, you know, functional analysis. It may be algebraic geometrical functional analysis will be necessary.
Excellent.
In the fixed.
That sounds like maybe 20 years of work, but but
many excellent people studies artificial intelligence. So its research speed is very rapidly now.
Yes. How
So
do you think we will compute the RLCT of a very large deep learning model? Is it hopeless?
also, but RLCT is a theoretical a theoretical concept that I think a mathematician will be able to calculate it because a mathematician I can study infinite dimensional objects. So I think it is not difficult for maybe not so difficult because, for example, Professor Miki Aoyagi in Nihon University clarified for RLCT of deep learning now. So maybe mathematicians will clarify so very large deep learning RLCT of deep learning. Thank you.
Very good.
If you have any times, so I recommend you to invite her to this conference. She will be clarified the RLCT for deep learning, for example.
Very good suggestion. Thank you. Yes, we will.
Would you mind if we take a photo of all of us at the computer all together? If we make a photo with us standing.
We'd like to take a kind of conference photo with you on the screen here and us standing around, if that's okay.
Sorry, I'm very plastic.
So just to hang on a second, we're going to stand up and stand around the TV. While
Yes,
people are getting up here, can I ask, in your book, Mathematical Theory of Bayesian Statistics, you make a comment about symmetry breaking. What were you thinking about there?
Yeah, symmetry breaking. So you maybe know the mathematical relation between symmetry breaking and phase transition in mathematical physics. Yeah, it is a very important concept in mathematical physics, and so maybe a singularity in so-called singularity in artificial intelligence has relation to symmetry breaking in statistical physics. So physics, many physics studies phase transitions in these models. Thus, a so-called singularity in artificial intelligence will be studied from statistical mechanics viewpoint.
Thank you.
Is this? Yeah, thank you.
Yeah. Okay, hang on a second. We're going to take a photo. We'll send it to you. Cheese. Yeah. Okay. Thank you very much, Professor. That was excellent. I enjoyed that very much.
Thank you for all. Thank you very much.
And thank you for doing beautiful work for 20 years or longer.
Yeah, thank you.
It's a great pleasure to read your work. Thank you very much.
Yeah. Okay, thank you very much.
Okay, goodbye.
Goodbye. So how to? Yeah, thank you.
Yeah. You hit the nail on that. Why is it not? Okay. You can end the meeting.